Okay, this is lecture 2. We're talking about memory, the 8086, 8088 memory. Regarding memory, the memory can be studied from 2 points of view. From the programmer's point of view, and we call this the logical memory. Programmers need only to know the size of the memory. In writing codes and programming your computers, a programmer should not go beyond the limit of the system's memory. Okay, he needs only to know the size of the memory. While from the point of view of the hardware designer, the memory is the physical memory. How this memory should be placed regarding their hardware. Do we need to leave the memory as one block or better be divided into different banks? The one who decides whether to leave it as is or to divide into different banks is the hardware engineer. For the 8086, 8088 memory, we know that the memory is 1 megabytes. We have a 20-bit address bus. A 20-bit address bus can access as many as 1 megabyte of memory. This is why the 1 megabyte has starting address of 20 zeros and ending address of 20 ones. In order to be able to access any byte inside this memory, we should give each and every byte an address starting from 20 zeros ending with 20 ones. Okay, inside this 1 megabyte of memory, there are some range of addresses that are dedicated for a special purpose. So you could see inside this 1 megabytes a range which is a reserved range or dedicated ranges of addresses. For example, this range of addresses is to be used for user interrupt codes. If you need to add an interrupt code, you have to give it an address. You take the available addresses from this range. And this is for future use. If you need to extend your system, you would need some memory locations, some addresses to help you extending your system. And here is for special functions. So these ranges of addresses are not to be used publicly, but this range is an open for public use. Okay, regarding the 8088 processor, we know that the data bus is composed of 8 bits. So the memory, the hardware designer better leave the memory as is in a one block and you consume one clock cycle in reading or writing memory locations from the memory to the data bus. This is the data bus, okay? So since the data bus is an 8-bit wide, so you have to consume a clock cycle to take 8 bits from memory to the data bus or vice versa. This is why it doesn't do you any good to break the memory into different banks, okay? Unlike the case of the 8086 processor, whose data bus is composed of 16 bits, so the hardware designer would better divide the 1 megabytes into two banks, a low bank and a high bank. A low bank starts from 0 and these memory locations are all even numbered. So 0, 2, 4 and so on. While the high bank starts from 1 and these memory locations have an odd numbered memory locations. They are odd numbered memory locations 0, 3, 5, 7 and so on. In a one clock cycle, this is your data bus, which is 16-bit. In a one clock cycle, you fill in your data bus with 16 bits. So you take a byte from here and at the same time a byte from here. So when you fill in this 16-bit data bus, In a clock cycle, you get an 8-bit from the low bank, assume it at the 0 address, and then another 8-bit from the high bank, assume it at a 1 address. So you take 8 bits at the 0 address, 8 bits at the 1 address, and you fill out your data bus width if you are reading from memory, and you do the opposite if you are writing to memory. So by doing so, your 8086 system would be much better than 8088 because you need two operations in an 8088 system to do this, to fill or to transfer 16 bits from memory to your ALU, for example, or vice versa. You need to consume 2 clock cycles because you can at most move 8 bits at a time because your data bus is an 8-bit wide, right? So your transfer 16 bits in one operation in your 8086 system, and you require two operations in the 8088 system. This is why your 8086 system will be better and run faster than the 8088 system. Register. We said the processor should have numerous number of registers inside the microprocessor chip beside your ALU to facilitate the operations in a faster way. Okay. Registers in 8086 and 8088 processors can be looked at by 4 different types. They are divided into 4 different types: the general purpose registers, the pointer and index registers, the segment registers, and flag registers. So these are the 4 different types of registers inside your 8088 and the 8086 processors. And each group of these 4 groups is dedicated for some function. For example, the general purpose registers. How many registers are in this group? 4 registers. There are 4 registers in this group. Okay, they are used as all other registers are used to temporarily store some data. So they store data temporarily. Okay, and again, we don't need to remind you of the usefulness of the registers. They are used to store data temporarily to help a processor do its operations in a much faster way because you don't consume much time in getting data from register to your ALU or vice versa. You don't go outside the microprocessor chip. You stay inside the microprocessor chip in dealing with registers. Okay, the general purpose registers, this group is composed of 4 16-bit registers. There are 4 16-bit registers. They are named AX for accumulator register, BX for base register, CX for count register, DX for data register. These 16-bit registers can be divided into 8 8-bit registers. So we go to AX and divide it into a lower byte and a higher byte and a lower byte. And we name the higher byte AH and the lower byte AL. So instead of dealing with a 16-bit register named AX, we can deal with 2 8-bit registers. One is named AH and the other one is named AL. And we do the same with BX, BH, BL, CH, CL, DH, DL. So the general purpose registers can be dealt with as 4 16-bit registers or 8 8-bit registers. Okay. Okay, what are the functions of each of these registers? Where can we use them for? Okay, AX is the accumulator. It is used to, as the name reflects, to accumulate data in. Whenever you do arithmetic or logic operations, the result is placed in AX. And if you are sending data outside your microprocessor or bringing data in, this has to go through AX, an I/O device. BX is the base register. It holds the base address of a memory location, or if you're dealing with an array of data, the beginning address of the array is also placed in BX. All right, CX is the count register. If you are doing some loop, okay, the number of iterations you need to go over the loop should be placed in CX. If you are to do 10 iterations, you place 10 in CX. Your code will be run 10 times and CX will monitor each time your loop is run. Okay, and if you have some operation like rotate or shift operations, the number of bits you need to rotate or to shift your data, this number should be placed in CX. If you need to shift it 4 bits, you place 4 in your CX. DX is the data register. If you're doing 16-bit multiplication, you need 32 bits to save the result in. An additional 16-bit, which is DX, helps you do this. And DX can also be used to hold the port number of an I/O device. Okay, the second group of registers is the pointers and index registers. How many do we have in this group? 5. We have 5 pointer and index registers. Stack pointer, base pointer, instruction pointer, destination index, and source index. 3 pointers and 2 indices. Okay, the first is the stack pointer. Stack pointer. As we will know later, the memory segment dedicated for the stack called the stack memory segment. You save in this stack memory segment the addresses of locations you go back to whenever you do some jump. If you are jumping from your main code, you jump to do and execute some other code. After finishing executing this second code, you will have to come back to where you left in the main code to notice the address of the next instruction is saved in the stack pointer, and the stack pointer register helps you follow these addresses. Okay, it is of a LIFO type memory, last in, first out. It has to be like this, because if you're doing some nested loops and you jumped from the first loop to some other location, second loop, third loop, when you come back, you have to go first to the outer loop, then the first inner, then the second inner. So last in, which is the outer loop address, should be first out because you go from outside in. This is why the stack memory has to be of a LIFO type memory. Okay, you have two dedicated instructions, push and pop. Push and pop are used whenever you need to store some data inside the stack, not the data memory segment, and to get it out by pop. So you store it in the stack by push, and you get it out from the stack by pop. And as a matter of fact, the stack segment memory, is 64K, and you need few locations of this stack to be used for return addresses. So the rest of the stack can be used to store regular data in, not addresses. And if you do this, you have another pointer, which is the base pointer register, to store data into the stack. So if you're storing addresses, return addresses, you use the stack pointer. If you are storing regular data, not addresses, inside the stack pointer, you use the base pointer. Okay, so any array of data stored in the stack memory segment can be accessed, written in, and read from by the help of the base pointer. Okay, and SI is the source index used whenever you deal with string instructions, instruction dealing with blocks of data. You use this SI register, this index register, to help you getting a data from somewhere, which is the source. All right, so address it by SI, and you place it in some destination by the help of DI, and usually are used with string instructions which deal with blocks of data. Okay, instruction pointer, as the name reflects, this is a pointer that points to the next instruction to be executed. Whenever you get an instruction, this IP is updated to point to the next instruction that has to be executed after finishing executing the current instruction. So the instruction pointer, I guess this instruction pointer, this name is used by Intel's engineers, while Motorola's engineers call it program counter, PC. So it is the same as PC in Motorola's terminologies. It's a register that holds the address of the next instruction to be executed. Every time you execute an instruction, your processor 8088 or 8086 has to update the value inside IP to point to the next instruction to be executed. Okay, now the third group of registers, which is the segment registers. Okay, memory, the 8088, 8086 systems memory is 1 megabyte. Okay, the chose to partition or divide this 1 megabyte into blocks or segments of 64K. So each segment has only 64K bytes out of these 1 megabytes. So all in all, you would have 16 different segments, each of 64K byte wide. All right, but not all these 16 memory segments should be active at a time. 4 of them only have to be active at a time. So your system can deal with as many as 4 memory segments at a time, no more than 4. And we'll know shortly what are these 4. A code segment, a segment which you store code in. A data segment, you store data in. A stack segment used for return addresses. It's of a LIFO type memory. And then extra segment whenever you need to store and deal with blocks of data with the string instructions, use this extra segment. So you can activate, or the system would activate, these 4 segments at a time. It opens up these segments to take the code from, data from, to store return addresses, and to deal with blocks of data. Okay. And each segment should have a unique addresses, 64K addresses, starting from a lower one, and you add to this lower one 64K different addresses to get to the upper one. Okay, so we have to have some registers to point to the starting address of each of these four segments. So with the code segment memory, with the code memory segment, you would have the code segment register to store the beginning address of this code memory segment. So you know where the code memory segment starts at. And with the data memory segment, you use the data segment register, DS. With the stack memory segment, you use the stack segment register to point to the lower address of the stack memory segment. With the extra memory segment, you have a fourth register called the ES register, the extra segment register, which points to the lower address of the extra memory segment. Okay. Okay, each one of these four registers are 16-bit wide registers. So CS, DS, SS, and ES are all 16-bit wide registers. Okay, this is the memory, the total memory of your 8086, 8088 system. It is divided into different segments, four of which are active at a time. The code segment, this is the range of a code segment. All right, this is the code segment register. If you look closer to this, the most four hexadecimal digits are stored inside CS, and you do the same with the data segment whose range is this. You take the most significant four decimal digits, the leftmost four different decimal digits stored in DS. You do the same with the extra, and you do the same with the stack. Good. If you look at the starting addresses of these four memory segments, you would notice that the least significant hexadecimal digit is a zero, 4 0 binaries. All right, and it has to be like this. This enables you to point to a 20-bit address using a 16-bit register. So you have to store only the most significant four hexadecimal digits inside your CS. And these addresses are known by logical addresses. To get the physical address of a certain segment, like the code segment, what is the physical address of the beginning memory location inside code segment? It is 10,000 hexadecimal. You have only 1,000 stored in CS, 16 bits, so you would have to add a zero. You have to add a zero. You have to multiply by 10 hexadecimal and add a zero to get the 20 bits required for the beginning address of some segment. Okay, this trick is used to save 4 bits in each register. So we are using a 16-bit register to refer to a 20-bit address. This is done by making sure that each beginning address ends with a 4 binary zeros. So you store the most significant 4 hexadecimal digits and you multiply this by 10 to get the physical address of a certain memory segment. Okay. So each beginning address should end with a 4 binary zeros. This enables you to use a 16-bit register to point to a 20-bit address. And here a table that tells you, okay, these are the beginning addresses stored in registers of certain memory segments. What you do to know the address range of this memory segment, you multiply this by 0 and you add 64. You multiply this by 10, you add a 0 and you add 64. You multiply this by 10, you add the hexadecimal 0 and you add 64K. So you get the range of addresses for each of these three different memory segments. Okay, now I guess we'll end. Okay, segment registers. Again, the segment that are addressed by the registers. Okay, if you are dealing with codes inside your code memory segments, you'll use the instruction pointer to point to the address of the instruction to be executed. Dealing with the data segment, memory segment, you will use these three registers to point to a specific piece of data inside your data memory segment. In the stack memory segment, you are going to use these pointers, the base pointer and the stack pointer. In the extra memory segment, use
Okay, each memory location inside any memory segment needs 20 bits to refer to. So we need a 20 bit to point to some address. But we don't have 20-bit registers. We have only 16-bit registers. And we see how to do this. This is a trick done by Intel's engineer. They make sure when they divide the memory into segments that the least significant hexadecimal digit is 0. So all starts with zeros. So you need to store only 16 bits. Then to get the physical address, you multiply by 10 hexadecimal. You add 4 zeros to the least significant 4 bits to get the physical address. This will save 4 bits for each of the registers. We'll see you now in lecture 3.